I'm going to speak about the paper A Scaling-invariant Algorithm for Linear Programming, whose running time only depends on the constraint matrix. This is joint work with Daniel Dadouche and Sophie Hauberts from CWI Amsterdam and Lazi Weg from LSE. The problem we are concerned about is linear programming. In standard form, we can write linear programs as follows. We aim to minimize a linear objective over equality constraints, linear equality constraints, and enforce non-negativity of x. On the right-hand side, we find the dual version of the problem. We state it in Primal-dual form because this will become important for the interior point methods that we're going to use to solve the problem. Now, for LPs with n variables and m constraints, and L being the encoding length of the input A, B, and C, we already have since the 70s and 80s weakly polynomial solvers in the ellipsoid method and interior point methods. That means we have algorithms that solve LP in runtime that is polynomial in n, m, and the bit complexity L. A big open question of the area is whether there exists a strongly polynomial algorithm, that is an algorithm that is polynomial in m and n, but does not depend on the bit complexity L of the problem. What we are interested in is an algorithm that has dependence on the constraint matrix only. That is, we don't allow dependence on the right-hand side B and the objective C. This has been done for combinatorial LP already in the 80s by Eva Tadeusz. So if the constraint matrix is integral and the subdeterminants are bounded by some delta, then her algorithm solves LP in time that is polynomial in m, n, and the logarithm of delta. Now note that for TU matrices, we have the delta is equal to 1. And therefore, for TU constraints, we already have that we have a strongly polynomial algorithm. And more generally, if the matrix entries are integral and polynomially bounded in n, then her algorithm is strongly polynomial. There is another algorithm whose runtime only depends on the constraint matrix, and that is the layers least squared interior point method by Vavassis and Ye from 1996. Their algorithm is polynomial in n and log chi bar, where chi bar is the condition number of the matrix that we are going to introduce now. Chi bar has been studied since the 60s, and it has multiple equivalent definitions and characterizations. One of them is the lifting cost definition, which is as follows. Chi bar is the minimum number m such that if I give you subset I of the variables and I give you a vector on this subset I of variables, and if then there exists an extension of this vector to the kernel of A, then there's also an extension such that the norm of the full vector of the extension is at most m times the norm of the vector on the variables on I. So as an example, if the kernel of A is a subspace of R4, and I give you the first two coordinates 2 and 1, then if there exists an extension to the third and fourth coordinate, then there's also an extension such that the norm is at most chi bar times the norm of the first two coordinates. Now what we note already is that this chi bar definition only depends on the kernel of the matrix A. Another thing to note is, which is especially important for weakly polynomial solvers, that chi bar is bounded in 2 to the bit complexity of the matrix A. To have a connection to Tadeusz's result, we see also that chi bar is polynomially bounded in delta, which is a result by Tunchel. And another result by Tunchel that is rather a negative one is that it is NP hard to approximate chi bar even within a factor of 2 to the poly n. Important to the algorithm of Vavassis and Ye, as well as to our algorithm, are interior point methods. What are interior point methods doing in general? Interior point methods are following a central path. So given a parameter mu that is non-negative, and assuming that the primal and dual feasible sets have non-empty interior, then there exists a unique primal-dual feasible pair of solutions such that for every coordinate, the product of the primal variable and the dual variable is exactly mu. Now the collection of these pairs for all mu's is defining an algebraic curve, which is the so-called central path. And interior point methods are now following this central path. Importantly, these interior point methods are going to be scaling invariant. That means if I rescale the columns of my constraint matrix A by a positive number, which is equivalent to multiplying my constraint matrix A from the right-hand side with a positive diagonal matrix, then interior point methods behave invariant under these rescalings. So there is a one-by-one correspondence of primal-dual feasible solutions under the original instance and the rescaled instance, and interior point methods maintain this one-by-one correspondence under any rescaling. But importantly, the algorithm by Vassos and Ye is not going to be scaling invariant. So the question is, if there exists a scaling invariant layers least squared method for linear programming. Another important thing to notice is that the condition number chi bar is as well not scaling invariant. Remember that the kernel of A defines the condition number chi bar, and the kernel changes if we rescale the columns of the matrix. So it makes sense to define a condition number chi bar star, which is the infimum of chi bar under all rescalings, and an algorithm that would be scaling invariant would automatically give an algorithm that is depending on chi bar star as opposed to chi bar. In the middle of the slide, you can find an example that chi bar star can be arbitrarily much smaller than chi bar. Prior work on finding a scaling invariant layers least squared interior point method has been done by Montero and Tsuchiya in 2005. They find a scaling invariant algorithm that finds only an epsilon approximate solution. And another paper by these authors and Lan in 2009 has another scaling invariant algorithm that finds an exact solution, but each iteration has a weakly polynomial dependence on B and C. What are our contributions? Our contributions are that we find a scaling invariant algorithm, a layers least squared method for interior point methods, and by that settling an open question posed by Montero and Tsuchiya. Furthermore, we improve the runtime. We show that the number of linear system solves we need is only n to the 2.5 and additional log factors, including chi bar star, as opposed to n to the 3.5, which was the runtime for the original by Vassos and Ye algorithm. And furthermore, we find nearly optimal rescaling of the constraint matrix A. That is, we find in strongly polynomial time a rescaling that approximates chi bar up to a factor that a polynomial in chi bar star. Note that by Tunchel, there cannot be an algorithm that finds or approximates chi bar up to a factor of 2 to the poly n. Before we give details of our algorithm, first, some basics on primal-dual interior point methods, and we begin by complementary slackness. So given the primal-dual version of the LP, we have that a primal-dual solution is optimal if and only if one of the primal and the dual variables is 0. And for weak duality, we have that the duality gap is given by the scalar product of S and X. And recall that on the central path, we have that for every coordinate S, I, Xi is going to be mu, so the duality gap on the central path is given by exactly n times mu. Now that means for path following methods that if we initialize somewhere high up for a big parameter mu on the central path, what we aim to do is to go down the central path to small parameters mu, which have small duality gap, and then the end of the central path will correspond to an optimal solution. And in the predictor corrector algorithm by Mizuno, Todd, and Ye, we alternate between predictor and corrector steps. That is, we begin somewhere in close proximity of the central path and try to move down on the central path as far as possible, subject to not moving too far away from the central path. What follows is then a corrector step that doesn't try to decrease the duality gap, but just tries to get closer to the central path. And repeating these alternating steps, it can be shown that within root n or O of root n iterations, we are able to decrease mu by a factor of 2, which already gives essentially the weakly polynomial analysis. Now, what is the system that we are solving in the predictor step? In the middle of the slide, you can find the standard system that is solved for the predictor step. So the first inequality is primal feasibility, the second inequality is dual feasibility, and the third corresponds to shooting down on the central path. And equivalently, this system can be phrased as a least squares problem. So on the primal side, we essentially have, subject to feasibility constraints, a weighted least squares problem, and the same we have for the dual side. Given this update direction, we apply this to our current vector, and this will give us the predictor step. Now, how does this path following look like in an algorithm? So we have here depicted 30 variables, primal and dual variables, primal in red and dual in blue. And running a few iterations, we nearly monotonically decrease the variables by following the central path. And at some point, we can essentially guess which variables are going to be positive in a primal optimal solution and which variables are going to be optimal in the dual optimal solution. And for weakly polynomial solvers, this is enough for some central path parameter that is roughly 2 to the minus O of bit complexity to round to an optimal solution. And there has been big progress on weakly polynomial solvers for linear programs in recent years, which is displayed here. Just to mention a few of the authors, we have Lee, Sitford, Song, and Vandenbrand, who authored multiple papers, and we have a group from Columbia University that published a paper in arXiv a month ago. So this rounding step works if you use the bit complexity of the problem, but Vavasas and Ye are not doing that. They do instead is they say, okay, let us partition the variables into 2 sets. And these sets, so the first set is the set with primal variables with large value, and the second set, which is n star, is going to be the set with dual high variables. And why are we doing that? The standard predictor step, so essentially this weighted least squares problem, is not going to set variables to 0, because minimum least squares problems don't correspond to essentially setting variables to 0. What they do is instead, they solve the problem on the primal side for n star first, disregarding what happens on b star, of course subject to feasibility. And note that if we find the correct partition, then the objective value of this system is going to be 0. Now, subject to the solution that we find here, we then solve, which can be seen on the lower half of the slide, the problem for b star. Note that if we find the correct partition, we find optimal solutions here. And this idea, this approach, can be extended to multiple layers. So let us sort the variables by primal value, and we create a new layer, whenever there's a big gap between consecutive variables. So we can have up to n layers, and then we solve layer for layer the least squares problem. So on the primal side, we start with the 5th layer, solve the least squares problem based on the optimal solution that we find here. We solve it for layer 4 and 3 and so on. And on the dual side, we do it in the opposite direction. We solve the problem first for layer 1, then for layer 2, and so on. An important thing to note already is that this procedure is not going to be scaling invariant. If I rescale the variables in layer 5 such that they are the biggest, then of course I would get a completely different layering. So here the question is, how can you make this scaling invariant? Before we explain how we make our algorithm scaling invariant, we need a new notion, and that is the circuit imbalance measure, which is essentially the combinatorial version of chi-bar. So we define the standard independence matroid on the columns of the matrix A and look at the circuits of this matroid. And now for a circuit which corresponds to a one-dimensional subspace, we look at this at kappa ij, which is defined as the ratio of the jth and the ith variable, and define the circuit's imbalance measure of the matroid or of the kernel of A as the maximum over all these kappa ij's. Note that whenever our instance is irreducible, that this kappa ij is well defined. So we will find a circuit that contains both I and j. And now see that, okay, for TU matrices, we will have that kappa is going to be 1. And in general, we have that kappa is bounded by delta, where delta is, recall, the maximum subdeterminant. So here again, we have the connection to the Tadish result. And what we've shown is that chi bar can be approximated polynomially with kappa, so with the circuit imbalance measure. And this allows us essentially to try to minimize or to focus on kappa instead of chi bar. Because here we can ask the same question: how can we find the rescaling that minimizes this circuit imbalance measure kappa? So we define kappa star to be the infimum of kappa AD, where D is again a positive definite diagonal matrix, which then leads to a rescaled instance AD. And here we have to observe the following. If we look at a cycle on the graph that has as vertices the nodes, and we look at the complete graph, and an edge has as weights the kappa ij of the end nodes of this edge, then a rescaling of the instance will leave the cycles or the product over the kappa ij's of the cycles unchanged. And then we have the theorem that kappa star is going to be the maximum mean cycle multiplicatively of this graph. So again, the graph is defined as vertices being the variables and edges. So it's a complete graph, and edges have weight of this imbalance between the two nodes, kappa ij. Okay, so what we can do is we can algorithmically approximate kappa star. Why only approximate? Because we don't know this edge weights, but we can show that we can approximate these edge weights up to a factor polynomial in kappa star, and therefore we can approximate the optimal rescaling up to a polynomial in kappa star. Now, having that, we are able to find a scaling invariant layers least squared algorithm. Namely, what we do is, instead of layering as Vavassis and Ye did by looking at the ratio of primal variables directly, we look at the scaling invariant quantity, that is kappa ij times the ratio of the variables. Because note that for any rescaling, kappa ij will change in the same way as the ratio, or in the inverse way of the change of the ratio of I and j. And what we do is we create a layer whenever this ratio is going to be too big. So whenever that is going to be bigger or equal than 1 over poly n, then we add an edge to the graph, and we look at the strongly connected components of this graph, and these strongly connected components of this graph will correspond to our layers. And if we now contract these layers, then we get an acyclic graph, and the layers are now given by the ordering, or by n ordering of this acyclic graph. And then we again apply this layered least squared algorithm, which in the big picture is the description of our algorithm. Now, how can we get the bound on the runtime of using this algorithm? We have a characterization of the central path. Namely, we can partition the central path into long, straight parts, which can be traversed with layers least squared steps. So where we create this layering. They are depicted on the right-hand side in black. And these long, straight parts are intersected by short, relatively curved parts. And by short, I mean that the length is bounded by chi bar, by something like chi bar to the n, where that means that this is the ratio between the parameter mu on the central path at the entrance, at the beginning of the curved part, and the parameter at the end of the curved part. And with the standard analysis for TR point methods, we can traverse this curved part in root n times logarithm of chi bar to the n iterations, which then means that we can traverse this curved part in, as stated here, n to the 1.5 log chi bar iterations. And importantly, we do make combinatorial progress while passing through such a curved part. Namely, at the beginning of such a curved part, we will have that one primal variable is much larger than, let's say, primal variable j is much larger than the variable I. And at the end of the curved part, we will have that forever j is going to be smaller than I for the remainder of the central path. So this combinatorial progress can only happen n squared times, and therefore after n squared of these events, our algorithm will terminate. Important to note is that we do not know which of these two variables are involved in such a so-called crossover event, because if we would know, then we could either project out the variable or we could set them to 0 and then recurse on a smaller instance. So this, of course, here is not a scaling invariant notion, but you can phrase the same thing in a scaling invariant manner by not saying that j is bigger than I, but j is bigger than kappa ij times xi. And then in a very close manner, you can argue that this same event will happen. And note now that this curved part is not having length chi bar to the end, but chi bar star to the end, which already then gives you the scale invariant analysis with chi bar replaced by chi bar star. What we do is we do not look at these events as distinct, separate events, but we use a more fine-grained potential to analyze the combinatorial progress that we make, and therefore we can, with some more analysis, replace this 3.5 with a 2.5 log n. This should finish the runtime analysis of our algorithm. Let me conclude with a few open questions. One open question would be the improvement on the running time of our algorithm. Note that I didn't make a statement of the total runtime, but just the iteration complexity. But with the recent progress for weakly polynomial solvers, we should be able to apply them directly to our algorithm to obtain fast runtimes as well. Note that 3 of the authors of this paper show in an upcoming paper that we can apply in a black box manner these weakly polynomial solvers directly to obtain strongly polynomial algorithms. Again, of course, in dependence on this condition number chi bar. Another very interesting open question would be the following. Alamignon, Boschimol, Gobert, and Josvik have shown that methods that just follow the central path are not going to be strongly polynomial. So if you want to obtain a strongly polynomial algorithm, then you would need to leave the central path. So how would you do that? Another open question would be, for classes of LP for which we already have strongly polynomial algorithms, can we show that our algorithm is also strongly polynomial for those as well? Note that chi bar can be, for example, for 2 VPI systems, so 2 variable per inequality systems, be unbounded, but maybe better analysis can show that our algorithm is strongly polynomial here as well. And then another question would be, can we show that the number of iterations is maybe bounded exponentially in n if we don't get the polynomial bound, of course. So anything that would not depend on chi bar, but really just the dimension of the problem.